All right, I'll take your attention now, thank you. I'll just preface this with, this is my first lecture. I've never lectured before, so you'll probably learn why PhD students don't lecture from this lecture. So I hope it goes all right. If you can't read anything at any point, shout. If you can't read the board because it's too small, come forwards. If you've got a question, put your hand up. I'll probably attend to it. If not, hold it for the end of the lecture, that's fine. Because I've not done this before, I don't know how to pace a lecture, so this might go too fast. But I've got a set stuff to cover, which is about PSPACE from a test. So yeah, but without further ado, we're going to talk about PSPACE. From last time, you should have seen the definition of PSPACE very informally. This is the class of problems that's solvable in polynomial space, hence PSPACE. And you saw the observation that P is contained within PSPACE. Right, and the very rough idea for this is that, well, in polynomial time, the most you can write to is polynomial many cells. You can move to the right and right, move to the right and right, etc., etc. You can only write to polynomial many cells. And so clearly, any problem solvable in P is now solvable in PSPACE. Is that okay? Right. So then, this lecture, we're going to talk more about PSPACE. The first is that you can count in PSPACE. It sounds very strange. What I mean is, in polynomial space, it's possible to count from 0 to 2 to the n minus 1, where n is some like linear value in polynomial space. So one can count from 0 to 2 to the n minus 1 in polynomial space. This is something you probably can't do in polynomial time because that's an exponential value. And we're going to be using this counter over and over again in this lecture. You'll probably see it beyond this lecture. So how does one do this? It's exactly what you would expect. Imagine you have n-bit tape. And if you start with the tape with all zeros, then you just do the usual binary increment procedure. So you can increment from 0 to 1, then to 2, then to 3, etc. until you reach 2 to the n minus 1, right? Like this is 1, 1, 1, 1, 1. I mean, it's pretty simple. Maybe you have a bit excess, right? So if you've got some content on the tape, and you want to add 1 to this thing, then you'll like try and add 1. This will then become 0, and you might have to carry. You can actually hide this carry bit in the state space of your Turing machine. So if you really want to, you can have a bonus like carry. And clearly this can be done in n maybe plus 1 many bits, right? You can count from 0 to n all the way through, so you see every single configuration, all zeros and all zeros and 1, and all zeros and 1 and a 0, etc. in polynomial space. It might seem really simple, but it will become very useful. I think one might call this an odometer, but don't worry about precise names for this thing. So we're going to use this to first show that SAT, in particular 3SAT, is in PSPACE. So more interestingly, claim 3SAT belongs to PSPACE. So suppose you are given a formula phi, and phi is over n variables. The very rough idea is we're just going to try every single assignment from 1x1 through xn, and we're going to try every assignment by using the counter. That's it. So using n bits of space, we can exhaustively enumerate all assignments to x1 through xn. The idea is, like, imagine that you call your counter, let's call this n-bit counter C, then the ith bit in C will tell you the assignment of the ith variable. So this is 1 implies xi is true, ci is 0 implies xi is false. Okay, so we've enumerated, like, we're going through assignments one by one, and we're using the same n bits to do this. We're not writing them back to back to back, otherwise we'd have an exponential number of bits, which is not the right idea. But we actually have to test the assignment. So on each iteration, check the value of phi on x1 through xn if any are true. So if you see x1 through xn assigned to make phi of x1 through xn true, immediately return true, because the point of 3SAT is to decide whether the formula is satisfiable. If you find a satisfying assignment, you want to say yes. If you don't, so if C takes values of all ones and you still haven't found a satisfying assignment, return false. Now, the important part is, how do I do this in PSPACE, right? Like, that's the whole point. So we know that checking whether a formula with its assignments is true or false can be done in polynomial time. So this can be checked in polynomial time. And by the observation, this can be achieved in polynomial space. So the image I have in my mind is I have an n-bit counter, and then I have some extra polynomial space that's just fixed, that I stick on the side for checking valuations. And in total, if this has polynomial size, this has linear size, the sum, the amount of bits in total that you require, still polynomial. Okay, does that make sense? So 3SAT is in PSPACE. Any questions so far? Okay, cool. So now we're going to use this to show that NP is contained in PSPACE. So it's a bit stronger than what we've seen already, right? We've seen P is in PSPACE. I'm now going to up the ante to show that NP is in PSPACE. And we're going to use this. So I will use this board. So I think it's listed as a theorem. Yes. Theorem. NP is contained in PSPACE. Okay, so consider, proof. That's what we're doing. Consider any problem. Let's say y in NP. We know that 3SAT is NP complete. So we can reduce our problem, y, to 3SAT. So y reduces in polynomial time to 3SAT. Let's say reduction function is f. So we're going to reduce our instance y to an instance of SAT, and then solve SAT in PSPACE And remembering that the reduction is polynomial time, which means the reduction can be computed in polynomial space. So first, for a candidate instance, y, which we're hoping to test as in y, compute in polynomial time, which is polynomial space, by the observation, I'll write it over here, f of y. Now, by claim 3 sat belongs to P space, we can decide whether the instance of 3 sat, right, the reduction of f on y, belongs to 3 sat in polynomial space. Well, clearly this was a card reduction, so since f of y belongs to 3 sat, if and only if y belongs to y, we can decide if y belongs to y in polynomial space. Does that make sense? Okay, fantastic. Any questions so far? All right. So the first bit's a bit easy, but like, have we seen anything that's like pretty tricky for P-space, right? Like we've talked about P, that's clearly inside of P-space. We now talk about NP, that's inside of P-space. So we've now got a little bit of a hierarchy going on, right? We've got P is contained in NP is contained in P-space. Okay, like let's look at something that's tricky for P-space. So I'm going to introduce a new problem to you called quantified satisfiability. If SAT is the canonical problem for NP, quantified satisfiability is the canonical problem for P-space. And it's rather ugly, so we're going to spend some time thinking about this problem. But first, I need to define it. So, quantified satisfiability, which is almost always called QSAT, and I'll be calling it QSAT from now on. So you're given, I'll make sure the notation matches, given y equal on, let's say, n variables x1 through xn is a Boolean formula in CNF. The question, does the quantified version of this formula hold? So that is whether there exists a value for x1 such that for all values for x2, there exists a value for x3 such that for all values of x4, etc., right? Until you get to, for all values of xn minus 1, there exists a value of xn. Here, I'm just going to highlight that we're assuming, without loss of generality, that n is odd. If you really want n to be even, then you can have another, like, for all n, and then you can make a trivial clause for it, and you forget about it. So we just care about n odd, just so we get it in this format with existential quantification on the extremes. Whether this holds. Okay? This is like clearly really tricky because like, what on earth have you got to, oh, I've got to, that's fun. You've got to actually quantify something. Right, that should make more sense. This is really tricky, right? Like, how on earth do you evaluate this? Like, you've got to check a lot, right? Like, you've got to have universal quantification about all the odds, right? Like x2, x4, x6. That's like a lot to do. Okay, hopefully the problem makes sense. The intuition for QSAT, like, what makes it tricky? So, I think like the way that Matthias likes to do it is through like a game perspective. So, imagine you have Alice, who's going to control the existential variables, and we're going to have Bob, who's going to control the universal variables. So, Alice thinks x1 is true or false. Then Bob picks, so I should just caveat this is just intuition. Just to help you kind of like mentally process this like beast of a problem. Bob picks a value for x2. Then Alice picks one for x3. And this continues, right, until Alice finally gets to pick the assignment of xn. Question? You want it a bit bigger? Okay. Can you read this at the moment? Yeah. Okay, I'll keep it slightly bigger than this. Okay, so like, what's the point? Well, Alice would like to select x1, x3, etc., so that no matter what Bob selects, Alice can get the formula evaluated on x1, x2 through xn to be true. So you can imagine this as like Bob is trying to play adversary. It's like Bob can pick anything, Alice like really wants to carefully pick values for x1, x3, etc. to make this formula true. Best to look at some examples. So I'll kill this just to get a feeling for it, because it's quite nasty. We're going to use small instances. Two examples are going to be very similar. We're going to look at the positive instance first. So, positive instance of QSAT. Maybe I've spoiled the fun by telling you it's positive. So, consider the three clauses x1 or x2 and x2 bar or x2 or x3 bar, and x1 bar, or x2 bar, or x3. So, like, why is this a positive instance? So we're going to have to look for a strategy for Alice, right? That's the theory. We're going to have to pick something for x1, so that no matter what x2 is assigned to, we can then pick something for x3, for which the formula is true. So, say Alice sets x1 as true. Okay, this first clause is happy. This is also happy, but we've got more variables, so we'll work it out later. And now we have to condition on all of Bob's choices. So if Bob sets x2 is true, well, okay, fine, this clause is already okay. This clause is now fine. But now this is false and this is false, so we should set x3 to be true. So then Alice sets x3 is true And then, yeah, sure, all three clauses are satisfied. That's good. But we haven't considered if Bob selects x2 as false. Well, okay, this first clause is still fine because x1 is true. But this clause is now the issue, right? Because x2 is now false, so we want x3 to also be false so that x3 bar is true. So Alice sets x3 equals false also. And then this final clause is fine, because Bob set x2 to be false, x2 bar is true, so the final clause is good. And so in either case, whether Bob sets x2 to be true or false, it doesn't matter. The formula is always true. Does that make sense? We're probably seeing now why this is a tough problem and why it's been brought up. So then let's look at a negative instance just to get a better feeling for things. It's going to look awfully similar. Similar enough that I should double check. So the first clause is the same. The second clause has x2 also negated, and the third clause is the same. Okay, why is this negative? So let's consider the options for Alice. So if Alice sets x1 is true, then Bob sets x2 is true, and let's have a look. So if x1 is true, this clause is fine, x2 is true, that's still fine. This clause still has x3 bar, x2 is true, so x2 bar is false. So Alice would like for this clause to hold, Alice would like to set x3 to be false. But if Alice sets x3 to be false, because x1 is true, this is false, because x2 is true, this is false, and because x3 was just set to false, this would be false. So this would then imply that x2 bar or x3 bar and x1 bar or x2 bar or x3 is just false, no matter what you choose. So, okay, this is sort of bad for Alice. So otherwise, if Alice sets x1 is false, Bob has a much easier time. Bob just sets x2 to be false. And then this implies that x1 and or x2 is false. You just fail the first clause because Alice stepped into making that clause false. So then indeed, you don't have that there exists x1 for all x2, there exists x3 for which this formula holds. Does that make sense? Okay. Any questions? Okay, so the next step, like why is this problem been brought up? We're going to show that QSAT is in PSPACE. It's a harder problem than you've seen before, so perhaps it's surprising that it's in PSPACE. We have to be very careful. I'm going to kill this board. So the idea is we're going to recursively enumerate over all possible assignments and branch into sub-problems based on whether the variable is existentially quantified or universally quantified, and then recompile afterwards. So the image that you should have, well, I'll first give the top level. So we're going to, what's the proof? Sketch, but it'll be quite detailed. we're going to recursively enumerate all possibilities. Like similar in style to the counter, but it's going to be a bit more involved. And when I say this, we're going to enumerate by saying, if we're at, let's say, variable x2, we're going to try setting it to be true, and then look at the subproblem where we only have variables x3 to xn. And then we're going to try setting x2 to be false, and then we're going to look at the subproblem with only variables x3 through xn. And we're going to recurse like this. We're going to make smaller and smaller instances of QSAT by kind of going through all assignments of x1 through x2 through x3 all the way down to xn. So it's going to kind of look like this. So you're going to build a tree. On the top level, you have an existentially quantified variable, right? So this is x1 is true, or x1 is false. And then you're going to have universally quantified variables. You're going to have x2 is true, and x2 is false. And the same here. X2 is true and x2 is false. And you're going to repeat, right? Then you're going to have x3 is true and x3 is false. And this would repeat for x4 and so on and so on. Okay? So, like, we're going to process this tree from left to right, trying all the assignments. Like, we need to justify why this works in PSPACE. Note that when you're checking whether this holds, you need to look at, so as you get to the bottom, you get smaller and smaller subproblems. When you have a node like this, want to decide if either subproblem holds. So, because this is an existentially quantified variable, you're happy with x1 being true, or you're happy with x1 being false. So if either subproblem returns true, you're happy. Whereas here, you want to decide if both subproblems hold. Right, because you want to check that the subproblems on x3 through xn hold for both x2 is set to true and x2 is set to false. But be careful, if you maintain this whole tree, this would be exponential space, right? Because the number of nodes in this tree is exponential in the number of variables. So we're not going to store the tree. Well, what we're going to store is we're going to store the partial evaluation of the tree as we go along. Think about if you've got to a certain point, right? Imagine you've got x1 set to be something. You're currently checking if x2 is set to something, etc. And then you're at a free variable xi, and it will continue. What this will look like in the tree is you are currently solving for this branch. You've guessed down here, etc. And then you're getting to a point where you're looking at xi. You don't need to remember all of the subproblems in the left of the tree because you've already solved it. All you need to know here was, did I set this to be true? Because it doesn't matter what happens below, the universal quantifier only needs to know, was this subproblem okay? So on the left of this tree, you only need to store one bit. And for the rest of it, you're only storing one bit for every subproblem. So the number of bits that you need to maintain is only proportional to the depth. It's actually the depth plus 1. So only store one bit of information per subproblem. This means the space required for tracking enumeration equals the depth of the tree, which is n bits. That's not the whole thing, right? Because every time you get to the bottom of the tree, you have a current assignment, right? And you've stored, once you've got to the bottom of the tree, you've stored all of the branches that you didn't take. So you'll store a 1 here, and then maybe a 0 down here, and you'll store 1 bit, and you get to the very bottom. And you now need to actually compute phi on the current evaluation x, or current evaluation x1 through xn. So at the bottom of the tree, you'll compute subproblems with no quantifications. Right, because you've set x1 to be, I don't know, true, x2 is false, etc., all the way up to xn, I don't know, is true. And then all you're doing is computing this. And we've said before that you can do that in polynomial time, so you can do that in polynomial space. But the key observation is we're going to reuse the same polynomial space every time we're computing the assignment, or computing the valuation, sorry. So, like, I've run out of space, but key point, reuse the space for computing the unquantified and so if you can do this in polynomial space, you have a fixed amount of polynomial space for computing the evaluations, and then you only need linear space to maintain your current enumeration within the tree. Yeah, sure, it takes a very long time, right? It's going to take at least exponential time, right? Because you're going through the whole tree. But I don't care. All I care about is the space that I use. Does that make sense? It's really important you reuse the space. Yes.
How do you remember which ones have you been through? Like?
So all you need to do is when you come up. Yeah, that's a really good point. You need a counter for that. So good point. So okay, additionally. Store counter. This counter will have n minus 1 over 2 bits, where the value ci is equal, or the value of ci implies the assignment of the current university quantified variable. So this is like x I, x what, 2i plus 1? No, just x 2i. Implies x2i's value. And so when you come back up, you need to increment the counter to try the next one. But when you do so, you need to branch into whether you non-deterministically branch for the existential variables. Does that make sense? So when you're coming, like once you get to the bottom, you need to increment this counter, that will tell you the next subproblem, and you repeat. You have to come back up. Maybe you have to like rewrite. So when you get here, maybe you see a 0, and then you clear this from memory. You write a 1 here because, or sorry, maybe you got a 1 here as well. You satisfy this, so you continue as such. Does that make sense? Okay.
So it's like a tree traverse away?
Yeah, but you can't store the whole tree.
Yeah.
You can't write down the whole thing, so you just want to maintain like where you are in the tree, and all you need to know to evaluate, for example, for a parent node, all you need to know is the values of its two children. You don't need to know the whole tree. So you bottom up, you evaluate the bottom layer, that will tell you the parent, then you repeat up like this. And so at this point, when you've evaluated the whole of this subproblem, you don't need to know the values, you just need to know the value at the top to be able to, and then you bring up to evaluate this, and then you can evaluate the parent for those two. Does that make sense? And you maintain like which assignment to the universal variables, because they're the ones you're iterating through, by maintaining a counter on top. You might be able to do it without the counter, but I think it's clearer with the counter. So you just increment the counter, that tells you the next assignment to the universal variables, and you go through one by one, asking existentially, like, oh, like what is x1, then x3, then x5. Does that make sense? Cool. So it's linear space for the enumeration, polynomial space for the evaluation, polynomial space overall. As a bit sketchy, but does that make sense? That's why I said proof sketch and not proof, because I knew it would turn into a kind of funky picture. Okay. Still, why QSAT, right? Like I haven't justified QSAT. Turns out that QSAT is PSPACE-complete. But like, what does PSPACE-complete even mean? You've seen NP-complete, but I mean, it's the same thing. So I'll define it here. Definition. PSPACE complete. The feeling is that it's going to be the subclass of problems that are like hard in PSPACE, and that's indeed what it is. So a problem Y is PSPACE complete if, firstly, Y belongs to PSPACE. You see it otherwise. And for all problems, sorry, for any problem, X in PSPACE, there is a polynomial time cut reduction to Y. And now, really important theorem that we are not going to prove. QSAT is PSPACE complete. So showing a master reduction for QSAT is a tall order. And it was first done, so the citation for this is it was Stockmayer and Mayer. In 1973. We're not going to prove it. I think Matthias might point you to a reference to read about it if you'd like to know more. You do not need to know how this works. You're just going to take it on faith that QSAT is PSPACE complete. So now we have a hard problem for QSAT. It's our normal one. I mean, really, the guts of it are hidden from you. Okay, so cool. Should have just about enough time. So I'm now going to go beyond PSPACE a little bit. So I'm going to show you that PSPACE is contained in exponential time. There are two proofs. One is easy and relies on PSPACE being relies on QSAT being PSPACE complete. One is conceptual and much cooler, but is a little bit harder. So to be clear, EXPTIME is this class of problems for which there is an exponential time function, right? So an exponential time Turing machine that decides these problems, just like P, but you've got exponential time. So, definition. X time, sometimes you'll see it as just X, I'll write X time for clarity. The class of problems solvable in exponential time. And theorem. PSPACE is contained in EXPTIME. So we've got kind of an interesting kind of trade-off going here. Like we've got non-determinism and polynomial time. Like polynomial space beats that, but you can trade that in for exponential time and you win again. So we've got even more to the hierarchy. Like, why does this hold? So The fun thing is, this algorithm runs in exponential time. You just enumerate through the whole tree. The tree has exponential size, like exactly 2 to the n minus 1 many nodes in this tree. And every evaluation can be done in polynomial time. So the previous algorithm, proof, previous algo for QSAT runs in poly with respect to the size of the formula times 2 to the n minus 1 time. This is exponential. Okay. But we also know that QSAT is complete for PSPACE, since QSAT is PSPACE-complete. If you'd like to decide any problem in QSAT, so given x in PSPACE, sorry, reduce in polynomial time even to QSAT, then decide, let's say the reduction function was f of the candidate instance x in x time using previous algorithm. And so then any problem in PSPACE is in exp time, right? Because you can reduce it to QSAT, and you've seen that QSAT can be decided in exponential time. So then any problem that's in PSPACE can be decided in exponential time. And so yeah, you can conclude that PSPACE is in exp time. I mean, I think this is like not really showing you much. I think there's a much prettier conceptual way of seeing this. So I don't think I have necessarily the time to write down the whole proof. I'll give you the idea. We'll call it proof 2. Much cooler proof 2. So imagine you have a problem in PSPACE. So there is a polynomial space Turing machine for deciding that problem. Give an instance to that polynomial space Turing machine and just let it run. Let it run for a while. Let it run for at least exponential time, in fact. You can do that, right? You can let it run for exponential time. If it's still running after exponential time, then you've probably seen 2 identical configurations. And if you've seen 2 identical configurations, you know that you're in a loop. And therefore, you know the machine isn't going to halt. And if it isn't going to halt, it's not going to decide the problem. So if your machine is still running after exponential time, it's not computing like whether your candidate instance x is in x. So you can just reject if it's still running. The existence of the knowledge that the machine is still running after exponential time implies non-termination. And that's enough to reject. So all you need to do is run the machine for exponential time. If at some point it halted and accepted, you're happy, you then accept. If at some point it halted and rejected, you also reject. But if it's still running, you know it will run forever. Why is that? Well, we need to count the number of configurations in a polynomial space Turing machine. So suppose your problem x belongs to PSPACE. You have a Turing machine with, let's say, size of Q many states. Let's say poly n many bits. And let's say capital sigma is the alphabet. Then number of configurations is bounded above by, well, you can have a certain control state, you can have a certain head position, and then you can have on every cell one of size of sigma many letters, and there are polynomially many cells. It's ugly, but this is an exponential. So there are exponentially many configurations. So what you should do is run the machine for exactly this many steps, plus 1. If then on that final iteration, you know you're still running, by pigeonhole principle, you must have seen 2 configurations earlier that lined up. If you've seen 2 configurations earlier that lined up, you're going to be non-terminating. So if still running implies non-terminating, or non-halting is probably better. Just reject. Because, well, a machine that doesn't hold doesn't compute anything. Does that make sense? Conceptually, much cooler than the first proof. Bit harder to actually formalize, which is why I've given it kind of in this rough idea. And so, to kind of like round everything off, like what's the like takeaway? What's the corollary of this? So I think there's space over here. So we've seen already that P is in NP. You've seen that a while ago now. You've seen today that NP is contained in P space. And you've seen 2 proofs of P space is in EXPTIME. But, and I won't give an example, I don't know if this is Mathias's job in future. P is not equal to EXPTIME. So there are problems that can be decided with exponential time that cannot be decided in polynomial time. Like, conceptually it seems believable, like surely there's something you can do in exponential time you can't do in polynomial time. But like all these inclusions are open problems. So this is open problem 1. This is open problem 2. This is open problem 3. The thing is, though, that if P does not equal EXPTIME, we know that P is a strict subset of EXPTIME. That means that one of these open problems is, like, can be decided, right? Like, one of these inequalities, one of these inclusions, one inclusion at least, is strict. We don't know which. That'd be fantastic if you find out which. In fact, I think the popular belief among, like, I don't know, theoretical computer scientists, at least like complexity theorists, is that they're all strict, i.e. P does not equal NP, NP does not equal P space, and P space does not equal EXPTIME, but yeah, they're open problems. Does that make sense? Are there any questions? Otherwise, that is everything for today.